my dinner.
All right, so the next one we have here is the Shingled Erasure code with our friends from Fujitsu. Looks like are here. So if one of you gentlemen would like to take a few minutes to talk about what you have here, and we can take it from there.
Hi. Hi everyone.
Hello.
My name is Takeshi Miyamae. And the blueprint title is Shingled Erasure Code. A summary. We have developed recovery efficient and adjustable erasure code named SHEC. And we have presented our intermediate result at a Usenix workshop HotDep 14 on October 5th. We would like to provide the result for Ceph community because we would like to get your feedback for our future work. And owners are following three members: Takeshi Miyamae, Takanori Nakao, and Kensuke Shiozawa. All owners work for Fujitsu Laboratories Limited. And our current status is we have a working prototype for Firefly, and it is currently being tested. And we think Firefly's erasure code plugin API and Crash algorithm are sufficient for our purposes. However, we have not started testing on Giant or Hammer yet. And I will explain detailed description. SHEC provides more various recovery efficient layouts than Reed Solomon codes. Especially, SHEC is recovery efficient in case of multiple disk failures. Figure 1 shows SHEC 1065. SHEC 1065 has 10 data chunks and 6 parity chunks, and the locality of each parity chunk is 5. And locality means each parity's length of calculation ranges. For example, and in the figure one, P1 is calculated from D1 to D5. P2 is calculated from D3 to D7. So we can confirm the locality is 5 easily. By the way, for instance, if D6 and D9 break out, SHEC will recover them with P3 and P4 because the union of calculation ranges is smaller than the other unions of calculation ranges. For instance, P2, P3, and P4, P5, and so on. And in this case, we must read only 6 data or parity chunks to recover D6 and D9. So in comparison with other methods, for example, Reed-Solomon code, our method is recovery efficient because Reed-Solomon code has global parities and it must read 10 data or parity chunks, but we only have to read 6 data or parity chunks. So our method is more recovery efficient.
And sorry, I have one quick question. In the case of the case of SHEC 1065, then you store 10 original data blocks and you store 6 additional parity blocks or shards.
Yes.
What's the 5 number is how many data blocks each shard or each parity covers? Is that what the 5 is?
Yes.
Okay.
Yes.
Okay.
Right.
Okay.
And next, we selected space efficiency, recovery efficiency, and durability as erasure code properties, and plotted Reed-Solomon code and SHEC layouts on each three-dimensional property maps. Figure 2 is the property map of Reed-Solomon codes. In this case, upper area of the chart is sparse because Reed-Solomon code doesn't have so many recovery efficient layouts. On the other hand, in case of SHEC, as figure 3 shows, the upper area is filled with SHEC specific codes. So, for example, the user who usually use RAID 6 are provided alternative recovery efficient codes like SHEC 652. Therefore, we conclude that SHEC is more adjustable than Reed-Solomon codes. By the way, in the next step, we'd like to extend SHEC's layout and capabilities that could offer additional benefits to those of MSLRC and Ceph LRC. MSLRC means Microsoft LRC, and Ceph LRC means Ceph Pyramid Code. We are anticipating the following benefits from those extensions. First, the extended SHEC layouts include Reed-Solomon codes and MSLRC, and they are all generated from a common parameter set. Second, the number of recovery efficient layouts is much larger than MSLRC or Ceph LRC. And finally, in case of Ceph cluster that is contained in a single data center, and which means that is not split over one. Recovery overhead is smaller than Ceph LRC. This is the end of our presentation. Any questions?
I assume there's, I probably should go look at the paper, but it sounds like the key advantage over the current LRC approach is that you can deal with multiple disk failures by still reading only a subset of the data and parity blocks. Is that right? Because currently with the current LRC, if you lose one disk, then you read just a subset of say 5 out of 15 or whatever. But if you lose 2, then you have to read all 15 or 10 or whatever, however many blocks to reconstruct. But here you only have to do 2. Is that right?
I'm sorry. I'm sorry.
Yeah.
So would you explain once more?
So it sounds like the main advantage over Ceph LRC is that you can repair a 2-disk failure by reading fewer shards or disks or blocks or whatever you call them.
Yes.
Yeah. Okay.
Yeah.
Is the recovery overhead about the same or similar as far as the amount of additional data?
In comparison, what?
So
LRC?
Yeah.
Microsoft LRC?
Or Ceph LRC. I haven't read that Microsoft one, so I'm not sure exactly how it works, but I'm guessing it's similar to what we did. But with regular LRC, we store say 3 more blocks, and we get 1/3 as many during recovery. So we trade storage for recovery efficiency, but only for 1 disk. So here you're storing 6 additional blocks. But I think maybe I just don't understand how to read the recovery efficiency on these plots to figure out. Because
in comparison, in case of normal SHEC, recovery efficiency and space efficiency is worse than normal MSLRC. But we would like to extend our layout, and the new layout has almost the same recovery efficiency and space efficiency. I made a mistake. May I explain from the start?
Yeah.
Yeah, and in case of normal SHEC, the worst property is space efficiency and durability. The recovery efficiency in case of multiple disk failures are good, but it is realized from the sacrifice of space efficiency or durability. So we would like to extend our layout and we would like to have almost the same ability with MSLRC.
Okay. So this is already, you've already implemented it with Firefly. You're testing with the Firefly plugin interface, and it works.
Yes.
So I'm just there are a couple API changes with Giant, but I don't think they're big. They're pretty. I don't think they're hard to adapt to. So I think we would be very interested in, adapting to the new plugin interface and integrating it.
Yeah, there was not much change. It's not a big deal at all.
Yeah.
Actually, it's strictly more powerful because of the LRC stuff, but if you don't pay attention to that, it's not important, but it's slightly more powerful, and I think that's all.
Yeah. Okay. Yeah, I mean, I think it would be great to merge this into the tree so that people can use it. I think the main thing that, well, there are two things. I think first you need to convert to the latest version of the API. So the first thing would be to switch to the new version of the API, and then the second thing, I think there needs to be a written description that explains when you would want to use it and what advantages it has over either straight Reed-Solomon or the LRC or something else, so that people know when it makes sense and when it doesn't make sense, and maybe what parameters they would want to use. Because if people are going to use it, they need to know why. So having a simple description of, the cases where it's going to have big advantages and what those advantages are.
Hey, just a quick question to make sure I understand what's going on. If you lose D1 and D2, is that recoverable?
Yes.
Yeah, because you have
D1 and
P1,
D2?
P5, P6. All covered.
D1 and D2. If you lose those two, is that recoverable?
Yes. We can recover it.
Because you have
From
P1, P5, and P6.
P1, yeah. Yes. We can SHEC can recover from P1 and P5, or P1 and P6, or P5 and P6.
No, I guess I'm misunderstanding. Okay, cool.
So I guess as long as you have at least as many parity blocks covering the range as you lost disks, then you're okay.
Cool. Okay.
But within a range of 5, you can lose, any given block is covered by 3. So within any series of 5, you can lose up to 3 disks.
Okay.
I think.
Yeah. Right.
Yeah. Okay.
You're right. Yes.
That's pretty cool. Pretty cool.
Thank you.
Mm-hmm.
And may I ask some questions?
Yes. Yeah.
Please do.
And my first question is the backward compatibility. Does plugin interface of Hammer have backward compatibility?
No. It's really close. It's not going to be hard to update it. Let me put it that way. This isn't more than an hour of work. including the time it takes to rebuild it. The primary difference is that we added the ability to reorder the data and parity chunks. For example, if you want to put parity 1 next to data 1, and parity 2 next to data 3, and parity 3 next to data 5 in the crush hierarchy, you can do that with the new version of the interface. That's the primary difference.
So I think what it means is that you would have a version for Firefly, and then you would have a slightly different version for Giant that just wires up to the slightly different interface, and we would have it in 2 different branches, and it would be pretty easy.
Yeah. Sorry about the lack of stability. We're just not quite ready to commit to an interface.
It's brand new. So, yeah.
But Sam, that ability to place parities at a certain location is.
I'm sorry? Oh yes, it is very important. It just doesn't. It doesn't make it hard to port. It just means that if you port it and don't fill in that method, you get the old behavior. That's all.
And SHEC could actually take advantage of it as well.
I'm sorry?
And this SHEC could also take advantage of that placement, that new.
Yes. Oh yeah, absolutely. Yes. That's why that's the primary difference, and they actually want it. So my guess is it won't be that big a deal for them to port.
It might be worth pointing out that there's one bit of work that we still need to do on the OSD, and that is offloading recovery work or whatever.
Right. So if you only need P4 to recover, well, let's say you only need P3 and P4 to recover D6 and D9, or whatever you need. The primary is actually going to read all of the pieces locally and then write them back out. It's not going to read any more than it needs to read. That's the good news. It's not going to rebuild the whole object. But if the primary happens to be in the wrong row, it's still going to cause you a network hop. So the work we need to do is a sequence of network transfers that perhaps you didn't want. So the next thing is that we need to cause whichever replica is actually being recovered to do the recovery locally, or to do the reconstruction locally. It's not a huge deal. It's just, not
another thing to do. Yep, and it's the same thing that we need to do for LRC for it to also take full advantage of the local part of the local recovery.
Right. And that shouldn't require a change on your part. When we ask the plugin, actually, it doesn't. We'll just pick one of the recoveries.
Yeah.
And tell that one to do it.
Yep.
Unless I'm wrong, in which case it will cause a change to the API. I don't think it will.
It shouldn't. I think it's. Yeah, because I think all the cost information is in the OSD and not in the. As far as deciding who the primary should be. Yeah. Right. Okay.
May I ask another question?
Mm-hmm.
And what is our requirements for committing our source code into main trunk? For example, do we need review process, predetermined test process?
You will want to provide unit tests for it. It's a little weird. You can talk to Loic about how he did his. The biggest thing is that we'd like our tautology tests to include tests for this as well, so that it'll run in our regression suite. That's a little more involved, but not hugely so. Again, we can work with you on that. Mainly though, just follow the style guide, which shouldn't be terribly difficult. Yeah.
I'm writing this down in the Etherpad, so you can go look at that after. And then submit. I'm guessing for this, we probably want to do another submodule. if the code for the SHEC is on GitHub or something, then we could do another submodule. If it's really small, then we can put it directly in the tree. But it's
For this, I'd rather do a subtree merge because it has backwards compatibility implications. This isn't just a matter of any SHEC will work. It needs to be backwards compatible or compatible with the last version of SHEC so that we don't break people's clusters, that kind of thing.
Yeah, but that's, I mean, the submodule does that.
I mean, sort of.
Yeah.
You don't. Yeah.
People love them.
For this kind of thing, I'd rather it were actually in tree.
Yeah. Okay.
Personally.
Yeah. Either way. Yeah. So I in the Etherpad, I wrote down a couple notes. I think it's probably move to the latest version of the API. Although it doesn't matter that much. Write something, just some short document that explains why you would use it, so that users know when to use this and not something else. And some basic unit tests, hopefully. And then we'll integrate, and then submit a pull request, and we can review it. I get pull request. Yeah. Sounds great.
Okay.
Cool.
Looks like we got about 4 minutes left. If there are any questions, prompt folks. We'll move on here.
Has SHEC been used in any other storage systems yet, or has this been pure research up until now?
There is a plan. There is not even.
Sorry for interruption. My name is Kensuke Shiozawa, working with Miyamae-san, and it is not planned for use in other storage appliances or anything at this point.
Cool.
And also, the last question is that is there any do you have to decide who is going to commit to this SHEC source code? Are we fully responsible for maintaining this at this point, or is there anybody who wishes to join us?
Well, I mean, I think you guys would be reviewing changes to it, certainly.
Okay.
Yeah, I mean, I think if some random person showed up and wanted to change the SHEC code, we would wait for you to okay it, because we're not going to be able to competently review or know whether that's a good change or not.
Although I'm sure Loic will probably get his hands dirty at some point.
Yeah. Yeah, and hopefully others will. Right? That's kind of the idea, but yeah.
Okay, looking forward to it. Thank you.
Yeah, awesome. Thank you.
All right, great.
Cool.